Since making my breadboard 8-bit CPU based on Ben Eater's video series, I've looked for ways to challenge myself by designing expansions and improvements to the CPU. I have already expanded the control lines and added increment registers to the system. However, the original design for the SAP1 has a limitation that most people start bumping up against rather quickly. It only has 16 bytes of RAM. In this video, I'll be going over a design and an implementation of a memory module for the breadboard CPU that expands the memory addressing to use 16 bits rather than the 4 bits of the original SAP1 design. So the big question is, why 64K of RAM and ROM? Admittedly, this was a bit of a debate for me. At first, I thought about doing an 8-bit address space, which would give me 256 bytes of RAM. But basically, I wanted more. So I thought about then doing a 10-bit address space, and in fact started to design it. This would give me 1K of RAM, and which is more than sufficient for a breadboard computer. However, as I started working on it, I realized that creating a 10-bit address scheme was just about as hard as creating a 16-bit address scheme. So I decided, why not? Go ahead and build a 464K address space and be able to leverage it all in the breadboard computer. This project ended up being pretty educational for me. The first challenge was figuring out how a 2-byte address was going to be managed across a 1-byte data bus. As I worked on that, I realized that the original SAP1 design, where the memory address register was the sole register communicating with the RAM, just wasn't going to work. I ended up having to introduce an address bus, which allowed both the program counter and the address register to be able to select what address was being read from or written to for the RAM at any given time. The other challenge was the fact that the RAM chip used its data lines for both reading and writing values. This required me to create some logic that arbitrated when the data lines were being used for reading and when the data lines were being used for writing. So there's a lot to go over here, so I'll be breaking this up into 2 videos. The first video, this video, I'll be going over the design of the memory module and how to build it. The next video, I'll go over how to integrate the memory module with the breadboard computer, update the microcode, and basically get it working. So let's get started. So what are my goals with building this 16-bit memory module for my breadboard computer? Well, the first goal is exactly how it sounds. I want to add a 16-bit memory space to my breadboard computer. Reasons are pretty straightforward. So I have more RAM, I have more memory to be able to write larger programs and do more interesting things with this computer. Now, this has some implications. Just because I'm adding a 16-bit memory space, I do have to change a few other things with the computer too. Prime amongst them is my program counter now needs to be a 16-bit program counter, and my memory address register now needs to be a 16-bit memory address register. Those both have some implications in the overall design, which I'll be going over later, but just wanted to point out, the prime goal here is to be able to have a 16-bit memory space to be able to work with. My second goal is that half of this memory space should be ROM. And the reason why I want ROM is so I can burn programs into it without having to be required to manually key them in for every aspect of the program. The original Eater breadboard computer was great in its simplicity, but one thing that got old rather quickly was sitting there manually keying in every single program whenever you turned on the computer. By having the program in ROM, you could very easily just program that ROM, and the program is there regardless if the computer is on or off, so that when you turn on the computer, the program would take off right away. This also has the implication that I would need to have an assembler to be able to create those ROM images. While it's true I probably could create that ROM image by manually editing a hex file directly and then just burning the hex file to the ROM, that gets annoying rather quickly, especially if you want to do anything of reasonable size. So having an assembler that could build the actual bytecode for my computer directly would be something that I would need. The third goal here is to maintain the ability to key a program in the RAM. I know I just said that I don't want to do that as a matter of requirement, but I'm still taking an evolutionary step here from what I had in the original Eater breadboard computer to what I'm building towards, and I'm not ready to kind of ditch the dip switches yet. So I want to maintain that ability as it was present in the original Eater design. The next goal is to enable the memory address register to be able to increment its address value. I realized early on that if an address is going to be 2 bytes, in this case it is, 16-bit memory space requires a 2-byte address, they're going to get stored across two consecutive memory addresses. And so if I'm going to be dealing with bytes in any way, I'm going to have to move from one memory address to the next memory address quite regularly. The computer does not yet have ability to do 16-bit arithmetic. That is, if I want to go from memory address 8000 to 8001, I have to add 1 to the current address in some capacity so that I can get that 8001 memory address. And while my computer does have an ALU, it's only an 8-bit ALU, so I don't have the ability yet to create 16-bit arithmetic. So enabling the memory address register to do this itself, to be able to simply increment the memory address that it currently is holding, solves all my problems. And it creates the ability to be able to deal with consecutive memory addresses and whatever I need to do within a computer. Fifth goal is to maintain use of an 8-bit wide data bus. Back in the 70s and 80s, we had a bunch of 8-bit CPUs like the Z80 and the TMS 9900 that actually had a 16-bit address bus, but they still had an 8-bit data bus. The reason was this: to minimize system costs. If they were to add a 16-bit data bus, they required twice the RAM to hold 2-byte words, and many other aspects of the system would require more integrated circuits also. So basically, it would be a more expensive computer. For my project, I pretty much have the same reason. By keeping the data bus at 8 bits, that simplifies a lot of things and minimizes the changes I need to make to the CPU. As a result, my costs are going to be less. So that's the reason for the goal. Now, I think it's also important to point out what is not in scope with this project. Because when adding this 16-bit memory address, you can kind of think there's a lot of things to be done here. And in fact, there are. But I want to take these things one at a time. So first and foremost, the first thing that's not in scope of this project is to update the instruction register to enable greater than 4-bit instructions. The original Eater SAP1 breadboard computer uses 4-bit instructions, as you know. I don't want to do the work for that yet. And that's work I can do later. I can update the computer to have 16-bit memory addressing, but still leverage 4-bit instructions. And so my next project after this will actually be to update the instruction register. But for now, I'm going to keep it as is and continue to use 4-bit instructions. However, the one obvious change here is that the memory addresses that any instruction has will not be held in the lower 4 bits of the instruction byte, as was done with the original SAP1 computer. That's going to have to change, but it doesn't require me to change the actual instruction register to make that work. Also, another thing that's not in scope is creating a more efficient means for inputting data into RAM other than a micro-switch technique that was used in the original SAP1 breadboard computer by Ben Eater. As I mentioned, it's not my goal to tackle that yet. I will tackle that later, try to come up with a better way of keying in data, either through a keyboard or some kind of keypad. But for now, I'm not solving that problem. So my focus with this project is to add the 16-bit memory space and do what's necessary to make that work. So the heart of this project is the RAM and ROM chip. It's the whole reason why we're building it is to be able to add 32K of RAM and 32K of ROM. For the ROM chip, I went with the same 28C256 32K byte EEPROM chip that I used for the control line expansion. For me, this is a known and understood chip, and it being an EEPROM will allow me to easily reprogram it, which is kind of the key feature I was looking for. For the RAM chip, there were many choices. What I ultimately went with was a UM61512A from UMC. The primary reason for selecting this chip is because basically I had some on hand. The reality is you can use most any 32K byte or larger RAM chip. There are some wiring differences between them, and so the actual implementation that you make would probably have to change slightly, but for the most part they work the same. One of the key features of this chip, and the reason why I used it, is that it's TTL compatible and it has 3-state outputs. That's important when it comes to building this computer, because we've already started off building this computer with TTL chips, and I want to maintain that compatibility. This RAM chip actually has 64K of RAM, but we only be using half of it. With some ingenuity, the full RAM contents could be made available by using some kind of baking scheme, but that is not in the goal of this project. One crazy thought I had is that later on, when I implement a stack pointer, it would actually point to the RAM in the unused 32K of this RAM chip. That way, the 32K of primary RAM is not impinged by the stack. We'll figure that out later when I work on a stack pointer, but that, again, that's not part of this project. So the next thing to figure out is how the memory is going to be laid out within this address space, the 64K address space that we have. As you know, for 64K or 16-bit address space, you basically have addresses from 0000 to FFFF in hex. So the question is where will the ROM reside and where will the RAM reside? To keep things simple, the memory map I'm going to use is that the ROM will reside in the first 32K of memory space, and the RAM will reside in the top 32K. The reason for this, the motivation is that when the computer is started, the program counter will be pointing at 0. And I want to have boot code ultimately in the ROM that will automatically bring up the computer in some desired state. So that boot code needs to be at 000. And so that's where the ROM's got to reside. Now, I can envision a future where I would want to do something more sophisticated with this. For example, if I ever start getting into memory mapped type devices, I may want to reserve a portion of this memory space to be specific to that memory map. But for now, that's not part of this project, and the goal is just to keep it simple. So the memory map will be a simple ROM on the bottom 32K and RAM on the top 32K. Given the simple memory map, the wiring of these chips end up being similarly simple. The lower 15 address lines of the system get wired to the lower 15 address lines of both the RAM chip and the ROM chip. Now, the question is, how do we activate the RAM chip when we are in addresses that is in the upper 32K of the 64K address space, and how do we activate the ROM chip when the address points to the lower 32K? That ends up being rather straightforward because the RAM chip has an enable line that's active high, and the ROM chip has an enable line that's active low. So I just wire the 16th address line straight into the enable line of both of these chips. So when the 16th address line is high, meaning that it pertains to an address that's in the upper 32K of the 64K address space, the RAM chip would be enabled and the ROM chip would be disabled. When the address line, the 16th address line is low, again, meaning that is pointing to one of the addresses in the lower 32K of the address space, the ROM chip would be enabled and the RAM chip would be disabled. Because both of these chips have three state outputs, when it's disabled, their data lines actually go into a high impedance state, and so we don't have to worry about bus contention due to one of these chips being active and the other chip being inactive. Since the memory module has a 16-bit address space, and I wish to make all of it available to the code, the program counter itself needs to be a 16-bit counter. This is accomplished by using four 74-161 4-bit counters. The design ends up being very similar to the original Ben Eater SAP1 program counter, but here we use four 4-bit counters rather than just one, as Ben Eater did. Another difference is in how the program counter reads data from the data bus for the purposes of the jump. Since the program counter is a 16-bit word and the data bus is 8-bit, setting the program counter value from the data bus will require two read operations. To signal a ring from the data bus, we have a program counter in signal right here. However, to indicate which of the low or high words that the data bus value should be read into, we also have what I refer to as a high-low signal that tells the overall program counter which of its bytes the data bus value should be read into. Now, to make this work, you can see I have some logic right here that takes into account whether the high-low signal is high or low. When it's high, we want to read the data bus value into the high byte of the program counter. When it's low, we want to read the data bus into the low byte of the program counter. And what this logic does is tells which chips to actually be active for a read operation in order to load the data bus value directly into the actual registers of the 74-161. The memory address register is used to load the address value from the data bus and then use that to indicate the address in memory that should be read. It's similar to what the memory address register is used for in the original Eater SAP1. Now, again, the memory addresses themselves are multi-byte values, basically 2 bytes for the full 16-bit address space. And it's expected we're going to increasingly want to read multiple consecutive bytes of data from memory. For example, a memory address itself is going to require 2 bytes in order to store it. And so in order to read a memory address from RAM or ROM, you're going to have to read one memory address and then the next one after it in order to kind of get the full value. So that means we will want to read consecutive bytes frequently. In order to accomplish that, I ended up creating the memory address register to be basically identical to the program counter. However, the increment operation is going to be used for different reasons. Whereas the program counter uses the increment operation to advance to the next address, as in, that is the next instruction we're going to use. The memory address register will allow increments to occur so that you can read the next byte of RAM. Similar operation, honestly, but used semantically differently. Figuring out how the program counter and the memory address register interacted with each other is where I had the first big design challenge. To understand this challenge, let's first review how memory addresses were managed in the original Ben Eater design. In the original design, the memory address register is the interface for anything that wants to fetch a value from memory. The program counter would set the memory address register, and so could the instruction register. All of this was done through the data bus. However, in a 16-bit address space with a 8-bit address bus, this design approach is problematic. The problem is due to the fact that the original SAP1 design, the memory address register, is the only entity that can drive the memory. The best way to explain this is to simply show it. Consider the LDA instruction, which loads into register A the value at a given memory address. With 16-bit addressing, the LDA instruction would be represented in 3 bytes. The first byte is the instruction code itself, and the next 2 bytes is the memory address of the value that should be loaded into register A. The problem arises in that loading the address into memory address register takes 2 steps. The following steps for the LDA instruction illustrates the problem. First, the program counter points to the instruction code for the LDA instruction. This address is loaded into the memory address register, and the memory value is loaded into the instruction register. Second, the program counter is incremented to now point at the first byte of the address of the value to be loaded into register A. This program counter address is loaded into the memory address register, and in turn, the first byte of the value's address is then written back into the low byte of the memory address register. Here, I'm using a little endian design, which is why the first byte in the address is actually the low byte of the address value. Third, the program counter is incremented again to point at the second byte of the address of the value to be loaded in register A. However, to fetch the next value in memory, this would require us to write into the memory address register, which is currently holding the low byte of the address of the value to be loaded into register A. Therein lies the problem. We have a collision here. To solve this problem, we introduced an address bus to the design. The basic approach to this design is that multiple entities can write to the address bus, but only one at a time. The memory will fetch the value at whatever address is being written to the address bus, and then write that value to the data bus. This means that both the program counter and memory address register can both write to the address bus, but obviously they should not do so at the same time. So let's revisit how the LDA instruction will perform using this new architecture. First, the program counter points to the instruction code for the LDA instruction. This address is written to the address bus so that the memory unit loads the corresponding memory value, and the memory value is loaded into the instruction register. Second, the program counter is incremented to now point at the first byte of the address of the value to be loaded into register A. This new address is written to the address bus so that the memory unit loads the corresponding memory value, which is the first byte of the address to the value that's going to be loaded into register A. The first byte of the value's address is written into the low byte of the memory address register. Third, the program counter is incremented again to point at the second byte of the address of the value to be loaded into register A. The new address is written to the address bus so that the memory unit loads the corresponding memory value, and the second byte is now written to the high byte of the memory address register. Fourth, now the memory address register is activated to write to the address bus, thus causing the memory to load the value that we want to read into register A. This value is written into the data bus, and register A loads it. So you see here that the memory address register and the program counter can independently drive the memory unit, allowing for either of them to be loaded with a 16-bit address across 2 steps from the 8-bit data bus. Certainly there are more steps here than the original Eater SAP1 design, but now we can load and manage 2 byte memory addresses. One thing I added to the address bus design was a way to output the address bus value to the data bus. This feature would enable performing arithmetic on the address value beyond the simple increments that the program counter and the memory address register currently enable. Admittedly, I don't have an immediate use for it, but it wasn't hard to add, and I figured that there might be some future utility to having this capability. The address bus connection to memory unit is actually arbitrated by a bunch of 74LS157 units. This is similar in design to the original Eater SAP1, and its purpose is to arbitrate what is actually controlling the address lines that the memory unit sees. This switch controls whether the address lines that control the memory ICs either comes from the address bus itself or a bunch of microswitches, much like the original design that the Eater SAP1 had. This allows for manual programming of the RAM. Now, admittedly, this is going to be a bit annoying in a 32K RAM space. You're not going to really switch through all 32K in any time-efficient manner, but I put it there as my design goals indicated that I didn't want to change the mode of which I do programming right now. I also do a bunch of pull-down resistors on the address bus itself to make sure that if nothing's actively writing to the address bus presents as a bunch of zeros to the memory ICs. Here's the fully built memory module. I'm going to give you a quick tour of it, but before I go over the details that we just talked about, I'll point out one more change that I made. Here I have the actual clock module that I'm going to be using with the breadboard computer once this is integrated into the full breadboard computer. This is actually the exact same clock module that was built in the Eater SAP1, except for one change. I replaced 2 of the 555 timers with one 5556 timer. All I did that for is because it reduces the footprint on the breadboard and allowed me to fit it all within what you see here. One other change I did make was the selection of the potentiometer here. I actually have 2 of them. The reason for that is that the original design called for a 1 mega ohm potentiometer. I like the form factor of these potentiometers a lot. They're much easier to turn and use, but the problem is that they only come in at most 100K ohm potentiometers. And so I end up using 2 so I can get up to a 200K resistor into the 555 clock module that I use here to kind of slow down the clock as I want. I can't get it all the way to 1 mega ohm, which the original design called for, which would have a really slow clock, but I didn't feel the need for a very slow clock, so this works for me. And I strongly prefer this form factor. It's easy to turn and use. Now for the rest of this, here you have the program counter in these 2 boards here and the memory address register in these 2 boards here. The reality is, since they're both electrically the same, I could actually make that the program counter and that the address register. However, it's just arbitrary. I picked that one and for the program counter, and I picked that one for the address register. They both feed into these 245s, which arbitrate which one is writing to the address bus. And the address bus is basically these purple wires here. These purple wires connect the lines from the program counters 245s to the address registers 245s. And then it all leads into these 74LS157s, which are used to select whether the address being written to the RAM and ROM chip is coming from the address bus itself or from these micro switches here. Of course, these 157s are controlled by the run program switch here. And when it's in program mode, the address value is coming from the micro switches, and when it's in run mode, the address value is coming from the address bus. These 157s then feed into these 245s here, which are used to arbitrate whether a value is being written to the data bus or not. That is, I had to design for the address bus out. These are what enable it. You may ask, why did I not put it next to the data bus, which is going to be going right here? It actually turns out easier to wire everything this way in this layout that I had. I did try it the other way, and the wires got a little too messy for me. So this works out better. I only need to run 8 lines from here to the data bus, as opposed to if I moved it around, I'd still have 16 lines I need to work into these 245s that go here. Here's the RAM chip. Here is the ROM chip. Here are the 74LS257s that I use to switch between these micro switches being used to program the RAM, or the data bus being used to program the RAM. Here is the little mini data bus that happens within the module between the RAM chips, the ROM chip, and these 257s. These logic chips here and here implement all the various logics that you saw in the designs, from arbitrating the high-low bit to control which one of these high or low bit bytes are being written to when you read in from the bus, to all the various other control signals. Right now I have the clock going. I can give you the example of getting the program counter ticking with the clock. Here is the program counter enable line. If I move it high, the program counter starts incrementing. We can do the same thing at the same time with the memory address register. Got to look for the address register enable. Here it is. If I move that high, the address register starts incrementing. I'll move it back low for now. You can control which one, the address register or the program counter, being writing to the address bus. Right now I'm going to move the address register out high, and now the address register is writing to the address bus, which is then selecting the address that's going to be selected from either the ROM or RAM. Since the high bit of the address is actually off, this is actually reading from a ROM address right now. I did program this ROM to simply put into its data the lower 8 bits of whatever address it has. So as the address register iterates through values, you should see these 8 bits equal to the lower 8 bits of the address, just because I programmed the ROM that way. Let's stop that and stop writing the address register to the address bus, and instead let's write the program counter to the address bus. The program counter is currently in the RAM regime because the high bit is on. So this is actually reading from RAM. The RAM is actually just junk right now. It's just whatever random state it came up in. We can put it into program mode and select a RAM address. Let's just put all values here. And actually, let's go to the 0 amp. And we can select a RAM address, and let's just start programming some values into the RAM address. I'm going to do some weird design here, where at this address I'll put 1. At the next address I will put this value, program that value in. And as I program it, one thing you should note is, given that logic I came to prevent bus contention, when I press this button, the RAM chip is actually disabled, and it's no longer writing to the data bus, and instead the 74LS257s are enabled, and it will start writing whatever value I have in these micro switches to the data bus, which then the RAM is put into write enable mode, and thus it will write the value on this data bus into its memory. When I let go of that switch, the inverse happens. The RAM gets the write enable gets disabled, these chips get disabled, and the RAM gets enabled, so it will start writing the value out. So when I go to this next address value here, and I put in this third pattern right here, right now these don't match. When I'm pressing and holding, the values you see on the LEDs there are coming from the micro switches, or more technically the 74LS257s writing the micro switch value to the internal data bus. When I let go, it immediately, the RAM has been programmed, these 257s got disabled, and now this value is actually being driven by the RAM itself, writing that same value back to the internal data bus here. So I'll go in and continue programming a few more of these just to demonstrate that it works. Okay, so let's go back into program run mode, but I'm going to disable the clock. I am going to first reset the program counter to be in basically the address 8000, which would be this bit on and everything else off. I have set, this is my bus simulation right here, data bus simulation. I have it set to the leftmost bit on. I'm going to first read in the high bit, so I put the high-low into positive, and then I'll do the program counter in to read that into the program counter. Put that to high. Of course, it's not read in yet because I need to clock it in. Press the clock button. You see it changes. Let's disable the program counter enable. You saw it kind of switch there. Don't want that. Okay, now for the lower byte, I will move the high-low to low to indicate I want to now read into the lower byte. I will take this high bit on the data bus and put it low because I want these all to be low, and then I still have the program counter in at high, so I'll clock that in, and now we have the program counter at address 8000. So let's put the program counter into off, and it doesn't matter what the high-low is when those are off. And let's turn the clock back on. The program counter enable is not on, but you will see that it's currently at the address 8000. It's writing that to the bus because we do have program counter out high. Since it's writing to the bus, it's selecting that address in RAM, and as you recall, I did program that to be the leftmost bit in RAM. Now, as I turn on the program counter enable and we start counting from this 8000 address 8000 and higher, what you should see is these bar graphs incrementing to the right. Like we go from 1 to 2 to 3 to 4 to 5 to 6 because that's how I programmed it. So let's turn that on and watch that happen. Here we go. And once you get past the address that I program, it starts showing junk again. So there you go. The memory module that I designed, it has been built and I've demonstrated it's working, and that's all I'm going to go over in this video. The next video, I'm going to actually integrate this with the rest of my breadboard computer, first by pulling out the original RAM module that was built as part of the Eater SAP1 build, and then replacing it with this memory module and also pulling out the original clock module. So that will all be in the next video. Thanks for joining me. I hope you enjoyed this video. If you did, please subscribe to the channel and like this video. I will be publishing the next video where I complete this memory module build and integrate it with the rest of the computer in a few weeks. So look forward to that. Goodbye for now.